the answer to this, by the way, this is a cadmium silver half cell, this reads. So realize that means I've got the cadmium metal, the silver metal, and the two solutions, electrolyte solutions that would go with that metal. Cadmium nitrate, silver nitrate. Cadmium silver cell. Everybody get it?
Yeah.
Or in real language, we would probably say this is a cadmium silver battery, or a lithium battery you've heard of, or a copper battery, hence the copper top on the Duracell battery, right? Copper zinc battery. So, but we don't say battery in sense, we say cells, so the cadmium silver half cell. So you are asked to do all of that stuff in that paragraph above. So where do you start? You start by identifying your strongest oxidizing agents and strongest reducing agents. And you probably found that your silver ion was your strongest oxidizing agent, did you?
Yes.
And that your cadmium metal was your strongest reducing agent, and you found those things in your data booklet, right? By going up the column and down the other column. Okay. So then when you get there, you go, right, well, strongest reducing agent, those are oxidized anode, these are reduced cathode. Can everybody do it that quickly? Or, if that doesn't suit your fancy, you found this one on the right-hand bottom corner, and those ones are Leo. So whatever shortcut you use, okay? And then, so if this is the anode, it's asked to start labeling them. So cadmium nitrate, two of them, silver nitrate, and silver. And the cadmium is your anode, and the silver will be your cathode, and the reaction happening at the cathode is this silver ion. Due to cell rotation, strongest, write the chemical equations to represent the cathode and the anode and the net cell reactions. So the reaction happening at the cathode is the Ag plus is gaining one electron to become Ag, and the cadmium is becoming cadmium 2 plus and 2 electrons. Is that correct?
Yes.
I need 2 of these happening because I've got 2 electrons. Am I going too fast for anybody? Everybody following along? And so the net reaction then is 2 Ag pluses, and a CD goes to 2 Ags and CD 2 plus. So there's a variety of ways of doing those half reactions. One is just recognizing that the ion's going to a metal and that this metal is going to an ion, and just writing them yourself, which is what I did. Because I don't have a data booklet in front of me. But you might have, when you look these up on your data booklet, written them like we did in chapter 12. This one writes that way, this one writes that way, and I just write them down on top of each other. Okay? It doesn't matter which way you've done it. And that's your net reaction. Then it asks you to label the electrodes. So, okay, so this is the silver electrode, and this is the cadmium electrode. Electrode. And label the electrodes, the electrolytes. These two are my electrolytes. And the electron flow. Electrons flow from everybody? Anode to cathode. Have you got that memorized yet? Electrons flow from the anode to the cathode. So because I've put the anode on the left here, there's my electron flow. It's going that way in the wire. Right? Electrons go in the wire. So in the wire, the electron flows from the anode to the cathode. And the ion movement, well, the cations are going to the cathode. My cations being my cadmium 2 plus, my silver 2 plus, and whatever I have in my salt bridge plus. And the anions are going the other way. Towards the anode. being the NO3 minuses in this case. Happy days, everybody? Okay, so the beauty of this unit is that this is all it is. And you just repeat it for every single example. They might get you to start somewhere different, but it's the same thing. The bad thing about this unit is that, you know, like when normally you learn something in school, you start with something easy and you work on something a little harder and then another step harder and then another step harder. You can't do that with this unit. It's just all of it. So the first one feels really awkward and really hard because you're kind of struggling with all of it. And the second one will feel easier because you're struggling with less of it. And hopefully by the end of today, you feel on top of all of it. But it's no different than that example right there. So hands up if you feel, looking at this example, now today, like that's easier than it was yesterday. Good. That's the way you want to feel. Okay? Lee, did you have a question?
Just the cell potential. I just want to make sure I had it calculated right.
Sorry. And then the electron cell potential, well, it's cathode minus anode. So I would look up in my data booklet. And I'm not going to worry about flipping the sign on this. I'm not going to worry about I could write them here, I could flip the sign, but I'm not going to this time. I'm simply going to look up my values in my data booklet. You could do it that way, by the way. I am not going to. Is what I'm saying.
You have to?
No, watch. Remember this equation from yesterday? You might not. Cathode minus anode. So the E for the cell. What does that funny symbol mean, by the way, everybody?
Electrical difference.
This one. Nope. What did it mean when we did
Change.
that?
Or a standard.
Standard.
Pressure.
Standard atmospheric pressure, temperature, and concentration. Same thing here. This is assuming standard temperature, atmosphere, pressure, except blah, blah. Okay. So cathode minus anode. So I'm looking up my silver and my cadmium, and I see the silver at the top. So if this is my data booklet here, I found my silver. It's at positive 0.8, and I found my cadmium. It's at negative 0.40, like this. And I'm going cathode minus anode, so that equals 100 or 1.1. What does it equal? 1.20. So cathode minus anode. So 0.8 minus negative 0.40 equals 1.20. Everybody get that? Now, if you chose to write the numbers beside here, you would have flipped this one. No, you wouldn't have. You would have flipped this one. Is that right? Let me just go back to the data booklet and have a look. Yeah, you would have flipped this one. So this one would have been positive 0.40. This one would have been positive 0.80, and you would have added them because you're adding your half reactions, and you would have still got 1.20, just like I did. Just like I did, folks.
So those two equations are ways are interchangeable?
Yes. Those two ways are interchangeable. You can do it either way. Okay? Chances are you will make less mistakes this way. Would you agree with that? Looking them up in the data booklet and just taking the top number, subtract the bottom number in your calculator. And not worrying about which one to flip and not worrying about the sign, nothing. You just take the two numbers as they are written in here and you are subtracting them. Okay? And it's also a lot easier if the question just asks, what is the cell potential for the following? Then you don't have to worry about which one's the cathode, which one's the stronger, which one's the weak. No, it's just top minus bottom. Done. Sorted. There's your answer. Okay? However, if they ask you to write it down, or if they ask you what is the oxidation potential, then you have to put it. Everybody understand what I did here, because it's the first time I've done it on a board. Happy? Okay. So then, the next one. Where's Kristen today? And I haven't done registration, have I?
She's at a showcase.
Okay.
I'm Lauren Meads this book.
Pardon?
Okay, that's second.
Okay, so just talking about the name of this one for a second. Iodic acid and zinc half cell. So the zinc half cell, because the previous example you would have guessed is the zinc metal and a zinc ion compound, right? Like zinc nitrate, for example, or zinc chloride even. But oh wait, is zinc chloride soluble? I'd have to look that up, right? Somebody use zinc nitrate because all nitrates are soluble. So that makes it easy. I don't have to look that one up. Okay, so that part should be okay, the zinc half cell bit, because it's everything we've done so far, metal in its solution. This acid part is not as easy for us. So iodic acid, which you'd have to look up, and you would have found out that it's HiO3. So what are the species involved in that? An H plus and an IO3 minus. Okay, but what metal? Because I need a stick, right? You need a stick. So what electrode, what stick do you put in there? Well, you don't want a metal that reacts, do you? You want an inert metal. And our two inert metals that we choose to grab from are either platinum or, what's the other inert metal we've been using in our examples? Carbon graphite. Okay, so you pick one of those two. And remembering it goes metal solution, double bond, solution, metal. So that's why you write the cell notation for that word. Are you okay with that? We're going to practice a few of those today. Okay, so let's just get rid of this so I've got some room on the board. Labeling everything. We're going to put our platinum here just because it's here. This is an electrode. It's an inert electrode. The solution inside that porous cup should be my iodic acid electrolyte. I'm missing a few words in there. Anyway, L-Y-T-E. This is your zinc, and this must be your zinc 2 plus. So it comes with something else, zinc nitrate, zinc sulfate, zinc something. It doesn't matter what it is. Electrolyte. So which is the cathode, which is the anode? You look up the two reactions, and you find that your H plus is your, tell me, strongest oxidizing agent, and therefore the zinc must be your strongest reducing agent. Is that correct?
Yeah.
And so you've got your zinc becoming zinc 2 plus and 2 electrons, and you've got your H pluses, 2 of them gaining 2 electrons to become H2 gas. Ready for that? The diagnostic test that we would see to make sure this is working. Can you tell me some diagnostic tests that I would be able to see? I would see bubbles. Everybody okay with that? Where are the bubbles coming from? Hydrogen gas being formed? Nod your head if you're with me. Okay, so what other diagnostic tests would I have?
Color change.
What color change?
Change in the solution of the electrolyte.
What color is zinc? Colorless. And what are you forming? More of it. So no. A good thought, but you can't just default to that. What other thing? Not Evan, because you guessed the first one. Somebody else? pH. Would there be a change in pH?
Well, it's getting more acidified because
No, less
or less acidified because the H plus is going to H2.
Right, good. Less acidified because I'm using up that H plus. So my pH should go up. Less acidified up. Opposite, yes? And one more diagnostic test.
Formation of the reciprocal.
Less and less.
Don't just pluck things out of the air. Look at what we've got happening. Not Daria, because she guessed the second one. Pardon?
Formation of gas.
We've already said that one. So we said the gas is forming, the acid is being used up. Come on, people. Thank you. Andy, a little louder. The mass change of the zinc should go up or down? Am I using it or creating zinc solid? Using, therefore the mass should go down. Yes, out there? Okay, okay, so come on you guys, you gotta practice those things, okay? You gotta practice those things. Okay, so, and then the net, it's 2 and 2, so I don't have to multiply anything. It would be zinc, 2H pluses, oopsies, goes to zinc 2 plus and H2 gas. And this is my loss of electrons oxidation anode reaction. This is my gain of electrons reduction, the reaction happening at the cathode. What is my cathode?
Platinum and iodic acid.
Yes. What is my cathode? It isn't the H plus. This is the reaction happening at the cathode. Where is that? It's in here, in this porous cup. So therefore it's this electrode that is the cathode. Everybody understand that? So the platinum is my cathode. This is my cathode, and this is the reaction gaining electrons. And this is my anode, and it is indeed reacting, so it is not inert. What else is last? The flow of electrons goes from the anode to the cathode, so the electrons are going this way. The solutions, so the cations are going this way. Cations into the porous cup, and the anions are going this way. Out of the porous cup, into the beaker. Does it ask for anything else? Oh, the voltage. Cathode minus anode. So the voltage is going to be that H plus, so that, sorry, let me write this properly. E naught for the cell will equal E naught for the cathode minus E naught for the anode. So the cathode in this case is the H plus reaction, minus the anode in this case is the zinc. And so this is 0, right? And this is, pardon? Negative 0.76, and so this reaction is positive 0.76 volts. Yes?
It's different here.
Oh, I gave you the answers.
Like this, I don't really like that.
Oh, okay, so that's fine. Ignore the answer. It's done with the different data booklet, so they've got a different reaction than we do. That's fine. Okay, this leads me to the point for today. Notice how there's something quite a little wrong with this. Is that zinc one correct? It's negative. So it's positive.
Yeah.
Okay. This leads me to this. This number that we ended up with is exactly how they got that number in your data booklet. They took every cell, the zinc half cell, and put it against a platinum H plus standard cell. And they took the voltage and they said, right, we're going to make this 0, this platinum one 0. So every one will just have that voltage that we got off of our voltmeter. Okay, so if you flip down your booklet to here, where do those cell potentials come from? Do you not have your booklet from? Oh, where do those cell potentials come from? First of all, I've stated, reminder, standard conditions, 1 atmosphere, 1 mole per liter, and 25 degrees Celsius. Just a little reminder, it's exact same as their delta H. Okay, but now solution concentrations play a major part because we didn't really talk about solutions and delta H's. So each half cell in your data booklet was measured against the standard hydrogen half cell, which looks like this. So here's a canister that's injecting H2 gas. There's your platinum electrode there. So this is just like an upside down test tube inside a beaker. So your upside down test tube has your platinum electrode. It's also got this wire thing going through, so I can then connect it to a voltmeter. And the solution in here is acidic at standard temperature and pressure. So what's in this? H plus and H2 gas. So it provides that line in your data booklet that has a voltage of 0. Right, that I just rubbed it on the board. H2 of them, 2 electrons, H2. That one, it's got a little of this and a little of this. So that we can hook it up to the zinc one. Zinc 2 plus 2 electrons goes to zinc, and I've got a little of this and a little of that in there. So where would that go? Well, voltmeter, stick, right? Salt bridge, another beaker. Oh, there we go, to zinc. This is zinc, and that's a zinc solution. And what would my voltmeter say? 76. 7.6. 0.76. 0.76. 0.76. Memory's nearly there, but not quite. Right? And so they just said, like, look, let's make these all 0. Arbitrarily. Arbitrarily, they made them 0. And it doesn't matter. The voltage was read, the number was given to the other half cell, so in my drawing zinc, and the 2 H pluses plus blah, 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 was given 0.00 volts. It's actually an infinite number of zeros. But because everything else is two significant figures, it just makes sense to record that as two significant figures. The arbitrary setting doesn't matter. We just scroll down. Because the electric potential difference is always a subtraction. So even if all the numbers were 20 volts higher, the subtraction would still be the same. So when I take a copper zinc, that waterfall would be the same difference. Even if it was 100 minus 200, it'd still be 100 difference. Or now I'm getting myself all confused. Or 500 to 400, it'd still be 100 difference. So because we're talking about a number line, it doesn't matter what number I arbitrarily set it at, because I'm always doing a subtraction, cathode minus anode. Okay? So, which takes us to this question here on 59. Assume that the reference half cell, so the scientists that did this for us and created these data booklets, saying, assume they didn't pick the hydrogen H plus cell to be 0. Let's pretend they picked the mercury 2 half cell. Okay? What would be the reduction potential of a standard chlorine half cell? So I need to go to my data booklet, and I need to find the mercury 2 half cell that's on here. Please be on here. Or not. So she very quickly grabs a textbook and hopes it's in there somewhere. Pardon? Did anybody else find it on that sheet?
Hd 2 plus 2 electrons for
Yep.
Hd.
Yes? Yes.
This is just in the
Near the top.
It's plus.
Tell me the number.
0.85.
Plus 0.85 volts? Okay. So plus 0.85. Oh, good. Yes, it is there. Okay? So it's saying, let's set that one to 0. So how would I set it to 0? I would have to subtract 0.85 from it to get it to 0. Everybody okay with that?
I don't get why we're saying
Because it's saying, let's say this is 0. The standard reference half cell is changed to the mercury one. So it's saying, look, mercury is no longer 0.85, it's now 0. what would the reduction potential standard be on a chlorine half cell? So when the reference half cell is hydrogen, chlorine is 1.36 volts. Everybody okay with that? But if I changed it to the mercury one, it wouldn't be 0.356, but it'd be 0.85 less than that. Because this is 0.85, so to get it to go to 0, I would have to subtract 0.85. And so that's exactly what I'm going to do with this one. Subtract 0.85 from it. Make sense? And so type that in your calculator, and what you get, positive, you have to record the positive, 0.71 volts. So if we were rewriting the data booklet and making mercury 0, we would have to write the chlorine to be 0.71 volts. Because the difference between chlorine and mercury would still be the same regardless. Does that make sense? Okay, so do B then. What about nickel?
Negative 0.26.
Negative 0.26. And so if the reference half cell wasn't hydrogen like the data booklet, but rather mercury, how would I need to change that number then? Subtract 0.85 from it. And so then what do you get? Are you following along? Do you understand, Raj? Could you do this on your own? The next question, if I asked you about the iron, if I said change it to iron half cell, could you do that? Okay. What would the net cell potential be on a chlorine nickel half cell? Or what did you get for an answer for B?
Negative 1.01.
Okay. What would the cell potential on a standard nickel chlorine half cell be? Well, the chlorine would be the cathode because it's got a more positive number, it'd be higher up on the data booklet. So this is 0.71 minus negative 1.01.
It's 1.11.
1.11? So I'm not 1.11 volts. Okay, and what do you get when you take cathode minus anode and you subtract those two numbers? You get 1.82 volts. Indicate you're positive. Everybody understand how you did C?
So you subtract the one that's higher up, but then you're not using the original number because it's the mercury.
Correct. Now, hold on a minute. Let's just do it like we would normally have done it. If I said, go to your data booklets and please tell me the voltage of a chlorine nickel cell. Okay, a standard chlorine nickel cell. You would have taken, what would you have taken? You'd have taken the chlorine, which is 1.36 volts, and the nickel, which is negative 0.26 volts, and you'd have subtracted them. Right? And your answer would have been positive 1.82 volts. Oh, it's the same. Why is it the same?
What's the difference?
Because it's a difference.
Because it's the difference. So because this is a difference, and this value between my fingers is 1.82, whether I'm subtracting them here on the number line or subtracting them here on the number line, it's still 1.82. You and your sibling, this is a hard concept for my brother, or for my sons to get, that my they're the brothers, my two sons, will always be 3 years apart. Always. and they do the math all the time. They're like, so that means when I'm 10, Carter will be 7? Like, it's amazing to them that they increase in age the same the whole way along. But that's what this is. It just feels different because it's 1 point and negatives and kind of crazy numbers, but it's the same concept. You're the same age difference between your siblings, no matter where on that year line you are. Okay? The end. Does that make sense? Couldn't you do that on your own? Because you'll need to. Yes?
Not equal 1.82, 1.36.
Well, you're adding them.
Yeah, but that'd be 1.6.
It sure looks like it would add to 0.6, wouldn't it?
Yeah.
0.62. That means the math somewhere along the way was wrong. Along the way. Because I'm trusting you guys to have done your math. So,
That's 0.51, which is
1.56 minus negative 0.26.
Why is it
Equals
0.5?
1.36 minus 0.85 is 0.51. Not 0.71.
this one is 0.51.
Yeah.
So this is 5.1. Okay, whoever's doing these numbers for me while I haven't got my calculator needs to have a calculator in their hand. I can do these in my head wrong too.
1.56.
No, it's 36.
Is it 36 or 5?
It's 36.
Well, then I put a 5.
I thought it was 5.
Oh, then it's not 0.71.
Yeah, it's
0.51,
we're good. It's 1.36.
Minus 0.85 equals, you guys have no hope for your 1.11 diploma, 1.62. Okay. Making that also 1.62. Okay? All right. Learn how to use a calculator.
Well,
Is
it's
there-
just
is there more
you're
with that?
threes and your fives. And your
Yeah.
So that's still 1. Wait, so does it equal?
It equals 1.62.
So the
There
first
it is.
answer to A equaled 0.51. The first answer to A is 0.51. Which means that when we do C, we're taking 0.51. Subtract negative 1.11. So we get positive 1.62. And when we take the net data booklet values, we also get positive 1.62. Okay. Happy?
Yeah.
Good. Question 2. Question 2 is no different than the one we just finished marking, the page 58, except for, number 1, it doesn't have a little picture diagram for you, and number 2, it doesn't have the chemicals with the cell notation. It has the words for the cell notation. So I'm going to do the first one for you in cell notation. What is the cobalt hydrogen standard cell? What are the chemicals involved in there then? Cobalt.
CO2.
And so cobalt would be a stick, right? What's the solution that must go with that stick? Cobalt nitrate. Or does it matter? No, so I might as well not cloud my judgment and I'll put CO2 plus.
Why? How do you know that it's 2 plus and not 3 plus?
Is there one bold-faced in your data booklet?
No.
They're both the same?
Yeah.
Which one's listed first?
2 plus.
That's the most common one. So it's the one that's listed first in your data booklet is the most common. And then what do I write next? Double line to indicate a salt bridge or porous cup. And then what's the solution that goes with the hydrogen standard cell?
Hydrogen plus.
H plus. Right? And probably a hydrochloric acid, sulfuric acid, but it doesn't matter. It's the H plus I'm concerned about. And then a line. And what stick am I going to put in there? Sure, platinum. Or graphite, carbon graphite. And now, So I've written the cell notation for you. Write the cell notation, that's what I've just done. Now label the electrodes. So figure out which is your strongest, figure out, oh, it wants cathode anode.
Oh, okay.
Wants cathode anode. And determine the cell potential. Can you do that on your own now? Other than Craig who's just walked in, but everyone else. Can everyone else do that on their own?
Yeah.
Okay, go then. And Craig, I'll come sit down with you for a second.